In this video, we'll understand semi-supervised learning in a simple, practical way. We'll see why machine learning often struggles when labeled data is limited, how unlabeled data can still help, and what assumptions make semi-supervised methods work. Along the way, we'll compare it with supervised and unsupervised learning and test your understanding with quick quizzes. Semi-supervised learning is a machine learning approach that combines the strengths of supervised and unsupervised learning. It trains models using a small amount of labeled data along with a larger amount of unlabeled data. This becomes very useful when collecting raw data is easy, but labeling that data takes time, money, or expert effort. For tasks like classification and regression, models usually need labeled examples. These labels act as ground truth, telling the model what the correct output should be. During training, a loss function checks how far the prediction is from the correct answer, and the model updates its weights to reduce that error. That is why this process is called supervised learning. Labeling sounds straightforward, but in practice it can become a major bottleneck. Even for image classification, you may need hundreds or thousands of examples. For object detection, humans must mark where objects are located. For segmentation, they may need to label pixel by pixel. And in areas like drug discovery or genetics, annotation can require deep domain expertise. So yes, labels are valuable, but they are also expensive. Now let us look at this in a simple table format.
Supervised vs unsupervised vs semi-supervised.
Main learning styles compared. Here is the core comparison from the article. Supervised learning depends fully on labeled data. Unsupervised learning works without labels at all. Semi-supervised learning sits in the middle, using both. That middle ground is exactly what makes it valuable when labels are scarce, but unlabeled data is abundant. In semi-supervised learning, a supervised algorithm often acts as the base learner. The labeled examples tell the model what classes exist and give it a reliable starting point. Then the unlabeled data adds extra structure and context, helping the model understand how samples are distributed. This can lead to a better decision boundary and stronger generalization. Now that we've covered core idea, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What kind of data does semi-supervised learning use? The correct answer is both labeled and unlabeled data. Semi-supervised learning combines a smaller labeled set with a larger unlabeled set. Question 2. Why is semi-supervised learning especially useful? The correct answer is when labeled data is expensive, but unlabeled data is available. That is the exact scenario where semi-supervised learning becomes practical and effective. Question 3. In supervised learning, what do labels mainly provide? The correct answer is ground truth. Labels tell the model the correct output, which helps compute loss and guide learning. A classification model tries to learn a decision boundary that separates one class from another. But if we train using very few labeled examples, the model may overfit those points and draw a poor boundary. Unlabeled data can reveal the actual shape of the data distribution, helping the boundary become more realistic and useful on real-world inputs. Unsupervised learning works without labeled data and usually without the same kind of loss setup used in supervised tasks. It can discover patterns, clusters, or structure, but it does not directly know what the correct class should be. That is why unsupervised learning alone may not be enough for classification, while semi-supervised learning can use a few labels to anchor the task. Self-supervised learning is closely related, but not identical. It creates learning tasks from the structure of unlabeled data itself, instead of using human-provided labels. These pretext tasks help the model learn useful representations. Later, a small labeled dataset can be used for supervised fine-tuning. So self-supervised learning often becomes part of a broader semi-supervised pipeline. Now that we've covered comparisons, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. What problem can happen if a supervised model has too few labeled examples? The correct answer is overfitting. With too few labeled points, the model may learn a boundary that fits training data but fails to generalize. Question 2. Which statement best describes unsupervised learning? The correct answer is, it uses neither labeled data nor external ground truth. Unsupervised learning discovers structure without human-provided labels. Question 3. What is a common role of self-supervised learning? The correct answer is pre-training representations. Self-supervised tasks help models learn useful representations from unlabeled data before fine-tuning. Semi-supervised learning does not mean any unlabeled data will help. The unlabeled examples must be relevant to the task. If you are training a cat versus dog classifier, unlabeled cat and dog images can help, but random images of horses or motorcycles may not. In fact, mismatched unlabeled data can reduce performance instead of improving it. Two important assumptions drive many semi-supervised methods. First, the cluster assumption says points in the same cluster likely belong to the same class. Second, the smoothness assumption says nearby points should have similar labels. This is powerful because a label from one point can effectively spread through nearby unlabeled points, helping the model infer structure beyond the small label set. The low-density assumption says the decision boundary should pass through regions with fewer data points, not cut through dense groups. The manifold assumption goes one step further, saying high-dimensional data often lies on lower-dimensional structures called manifolds. If the model captures that structure well, it can make better use of unlabeled samples and learn more meaningful class separation. Now that we've covered SSL assumptions, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. Which condition is necessary for unlabeled data to help in semi-supervised learning? The correct answer is, it must be relevant to the task. Semi-supervised learning works best when the unlabeled data comes from the same meaningful distribution as the task. Question 2. What does the smoothness assumption suggest? The correct answer is, nearby points likely share labels. The smoothness assumption says points close in input space should usually have the same label. Question 3. According to the low-density assumption, where should the decision boundary lie? The correct answer is, in sparse regions. A good boundary should avoid cutting through high-density areas where many similar points exist. That's the big picture of semi-supervised learning. If you understood why unlabeled data can be useful only when it is relevant, and how a few labels can guide a much larger dataset, then you've got the core idea. See you in the next lesson.